A warm greetings to one and all. In this session, let's learn about sequential data and Markov model. Sequential data are data points that occur in a specific order and they are time dependent. Example, daily rainfall measures, speech recognition, and so on. There are two categories, namely stationary distribution. These are the generative process that does not change over the time, whereas non-stationary distributions changes over the time. This assumption allows us to express the likelihood function as the product overall data points of the probability distribution evaluated at each data point. For sequential data, this assumption does not hold, as nearby data points are often correlated. Example, predicting whether it will rain tomorrow based on today's weather. Independent and identical distribution. Here the data points were treated as independent and identical distribution because we can see here the data point x1, x2, x3 and x4 were present independently. And the value of one observation does not affect the other data point. This corresponds to the graph without any connections between the observation. We can see here there is no link between the data points. It is the most basic way to model a sequence of data where each data point is assumed to come from same distribution, but there is no relationship between them. Modeling dependencies on all past observations would become complex, so Markov model simplified this by considering only the most recent observations to make predictions. Markov process is a simple stochastic process in which the distribution of future states depends only on the present state and not on how it arrived in the present state. A random sequence has Markov property if its distribution is determined based on its current state. Any random process having this property is called as Markov random process. For observable state sequence, this leads to Markov chain model. For non-observable states, this leads to hidden Markov model, that is HMM. Now let's learn about first order Markov chain. In first order Markov chain, the current state depends only on the previous state. That is, let's consider the data point x1, x2, x3 and x4. Here the current state of data point x4 depends on the previous state, that is x3 data point. Now this x3 data point depends on the previous state, that is x2 data point. Similarly, x2 depends on the previous state, that is the data point x1. First order Markov chain is described as each observation being independent of all previous observation except the most recent. Example, let's consider predicting weather based on whether it rained the day before. The product rule to express the joint distribution for a sequence of observations in the form probability of x1, x2, x3 up to xn is equal to probability of x1 into probability of x2 given x1 into probability of x3 given x2 up to probability of xn given xn minus 1. This can be written as probability of x1, x2 up to xn is equal to probability of x1 product of I is equal to 2 to n probability of xi given xi minus 1. Second order Markov chain is also called as higher order Markov model. Here, the probability of transitioning to the next state depends on the two most recent states. So let's check out this diagram where we have the data points x1, x2, x3 and x4. Here, the data point x4 depends on the two most recent states, that is x3 and also x2. Similarly, let's consider x3. It depends on x2 and also on x1. So in mathematical terms, for the sequence of random variables x1, x2 up to xn, the second order Markov model property can be defined as probability of xn plus 1 given x1, x2 up to xn. That is, the probability of x4 given x1, x2 up to x3. That is xn, since it is xn plus 1. which is equivalent to probability of xn plus 1, that is x4, given xn comma xn minus 1. So x4 given xn is nothing but x3 comma xn minus 1, that is x2. So hope you are clear in this mathematical term. So this can be expressed as probability of x1, x2 up to xn is equal to probability of x1 into probability of x2 given x1, such that I is equivalent to 3 to n probability of xi given xi minus 2 comma xi minus 1. The second order Markov chain is useful when the next state depends not only on the present state but also on the recent past, which may be important in certain processes where history beyond the current state has a significant influence. Despite of increasing the complexity, the second order Markov model chain provides more flexibility and can model process where the current state alone is not sufficient to predict the future outcomes. Challenges in higher order Markov chain are it increases the complexity, that is, considering more previous observations makes the model more complex. It exponentially growth of parameter, that is, as the order increases, the number of parameters that needs to be estimated grows exponentially, making these models computationally expensive and hard to estimate for larger data set. Parameter requirements. Here, in an mth order Markov model, the k possible states of each observation, the number of parameters needed is proportional to k to the power of m minus 1. Impractically for a large m, that is, as m increases, that is, order of Markov model increases, the number of parameters increases rapidly. That is, this makes the model impractical for large values of m. Overfitting. With increasing complexity, there is a higher risk of overfitting the model to train the data, making it less generalizable to new data. In order to avoid the challenges, higher order Markov models can use parametric model with assumptions. First one is simplify structure, that is, assume specific distribution like Gaussian distribution or whatever it is required for the application in order to reduce the number of parameters. Next, dimensionality reduction. We can apply the techniques like PCA to reduce the feature space, simplifying the model and preventing the overfitting. We can introduce the latent variables also. By introducing the latent variables and its model, we can use hidden or unobserved variables to explain dependencies, reducing direct connection between the observed state. Hidden Markov models, that is, we can employ hidden Markov models to capture complex dynamics with fewer parameters by introducing latent or hidden states that influencing the observations. Now let's learn about latent variables and higher order Markov models. If we wish to build a model for sequences that is not limited by the Markov assumptions to any order and yet that can be specified using a limited number of free parameters. This can be achieved by introducing additional latent variables to permit a rich class of models to be constructed out of simple components with mixture distribution and continuous latent variables model. For each observation xn, we introduce a corresponding latent variable zn. Assume that it is the latent variable from form a Markov chain given rising to the graphical structure which is known as state space model. Here, let's consider data point x1, x2, xn minus 1, xn, xn plus 1 where observed data and z1, z2, zn minus 1, zn and zn plus 1 were latent variables. Latent variables cannot be observed directly. We have to assume as if they were existing. We can notice that there is no direct dependencies between the observed data, but observed data depends on its hidden variable, and the hidden variable depends on its previous state, as given in this diagram. The joint distribution for this model is given by probability of x1, x2 up to xn, z1, z2 up to Zn. Probability of Z1 into product of I is equal to 1 to n probability of Zi given Zi minus 1 into product of I is equal to 1 to n probability of Xi given Zi, where probability of Z1 is nothing but the probability of first latent variable and product of I is equal to 2 to n probability of Zi given Zi minus 1 is nothing but the first order Markov process which governs the latent variables. Similarly, product of I is equal to 1 to n product probability of Xi given Zi is conditional probability for each observed variable given its corresponding latent variable. So hope you are clear then latent variables which is used in higher order Markov models. Thank you all.